Good evening, Aylesbury. This is the beginning of everything. As you can hopefully see from the subtitle, I'm going to be talking about the origin and the very early history of the universe. When we look out into the universe, we see, let me just get that video to run. When we look out into the universe, we see billions, if not trillions, of galaxies. This looks like a little bit of CGI. It's really a 3D atlas. Many millions of galaxies have had their positions on the sky measured and their distances measured, and hence we can construct a 3D atlas. And this is a fly-through of that atlas. And it shows us not only that there are many, many galaxies out there, it also shows us that they are not uniformly distributed. We see them occasionally clumped together. Every once in a while, these clumps appear to be stretched out on what we call filaments. And there are some regions that are seen to be relatively sparsely populated with galaxies, so-called voids, relatively large volumes that have very low density of galaxies. So it's very clumpy out there. There's a sort of cosmic web, if you like, of filaments made up of galaxies and clusters of galaxies, and where these filaments intersect with each other, we get high densities. So we can ask ourselves, okay, there's lots of stuff out there, billions of galaxies, each of which probably contain many, many billions of stars. And there's a whole load of gas and dust as well. But where did all this stuff come from? That's what I'm addressing this evening. We've taken lots of snapshots of the sky, such as Hubble Deep Field, for instance, in which a snapshot of a very small patch of sky has showed us billions of galaxies, or at least showed us that there are billions of galaxies out there. There might be a few thousand on an image like this. Some are quite close, some are quite distant. And of course, because of the finite speed of light, with the more distant galaxies, light has taken a long time to reach us, so in a sense we're looking back in time at some of the more distant galaxies. So what is it I'm talking about this evening? I'm talking about the creation of the universe. When did this happen? Our best estimate is that that happened 13.8 billion years ago. Sometimes you get the question, how long did it take to make the universe? Well, the answer is about 3 minutes, and we'll see why that 3 minutes is important in due course. Another common question is, where did it happen? Well, you have to bear in mind that you can't think of the universe coming into existence at a particular point in space. You can't imagine it happened over there. Basically, we're talking about the creation of everything, and therefore it happened everywhere. Why did the universe evolve the way it did from its creation to what we see today? Well, basically, that's what we call the laws of physics. How do we know all this? Same answer, because of the laws of physics. Now, if we wanted to know what were the rules of the game for a game like chess, in a sense, that's the same question as what are the rules of the game of the universe? The rules of the game of the universe are the laws of physics, but how do we know what they are? How do we know how the universe came into being and how it's evolved? If we had this snapshot of a game, we might be asked, can we tell what the rules of the game are from this picture? And the answer is basically no. We might be able to guess that some of these pieces are coloured gold and some of them are coloured silver. So maybe it's a game between two people, but we can't really tell. In much the same way, if we take a snapshot of a galaxy, we can't really tell how that galaxy came to be and how it's evolving, what it used to look like billions of years in the past and what it might look like billions of years into the future. You might say with a game of chess, well, yeah, a snapshot isn't enough, but what if we watched two people playing chess? Could we then get an idea of the rules of the game? Well, yes, indeed. If we could watch people playing, then we could see how the pieces move. But we can't really watch a galaxy evolving. It might take 100 million years for the galaxy simply to rotate once. and we simply haven't got the patience. So the alternative is to say, well, if we can't have a video of a game being played, what if we could at least have a snapshot of 1 million games all being played, some of them early in the game, some of them later in the game? Well, yes, if we had enough information, if we could see snapshots of a large enough number of games being played, then we would have a chance of working out what the rules are, assuming the rules are the same for every chessboard that we would look at. And the same argument applies to galaxies. Looking at one galaxy is not enough. But if we look at thousands of galaxies, or millions of galaxies, or billions of galaxies, all remember at different times in their evolution, because the closer ones we're looking at relatively recently, the more distant ones we're looking at in the more distant past. It doesn't really matter whether we're talking about a Hubble deep field or a James Webb deep field. The principle is still the same. If we take enough images and get enough data from enough galaxies, then we can get an idea of how the universe has evolved. But when we look on a local scale, let alone the largest scales, when we look on a small scale, what's going on inside our galaxy, we might think, well, this is far too complex to get an idea of what's actually happening here. This is just a tiny part of a big hydrogen cloud. Some of you might recognize it as part of the constellation of Orion, with the Horsehead Nebula at the bottom and the Orion Nebula off to the top right. You might look at this and think it's too complex to work out what the rules of the game are. But we shouldn't fall into the trap of thinking just because something looks very complicated, that doesn't necessarily mean the rules of the game are too difficult to comprehend. For instance, if we think of this mathematical collection of points, it's a very small part, of a collection of mathematical points called a Mandelbrot set. We can zoom into this Mandelbrot set, and if we wished, we could keep zooming in indefinitely, and we would see more and more and more detail. Each pixel in this image has been coloured according to a mathematical formula. And even though there are, in principle, an infinite number of pixels in this set, we're only limited not by the mathematics of how we define this set, we're only limited by the power of the computer that allows us to calculate the colour of each and every pixel in the trillions and trillions and trillions of pixels that we're capable of calculating. You might ask yourself, well, isn't part of this a repeating pattern? Well, no, some parts appear to be a sort of repeating motif, but none of them are actually the same. In much the same way that stars in a galaxy, a number of stars, maybe millions of stars, might look similar to each other, but they're not actually the same. So how complex is the mathematical formula that allows us to calculate not simply the million or so pixels that you see in front of you at the moment? How complex is the mathematical formula that would allow us to calculate trillions upon trillions upon trillions of pixels like this? Well, the mathematical formula that generates the Mandelbrot set is that. I'm not going to explain how it does it, but that's basically it. So a very simple mathematical formula allows us to calculate extremely complex collections of objects. And just because this is a mathematical collection rather than a physical collection, well, it doesn't really matter. One of my favourite quotes from Einstein is this one. Basically, he's saying complexity is not the same thing as incomprehensibility. Yes, the universe is very complex, but the most incomprehensible thing about the world, or the universe if you prefer, is the fact that it is comprehensible. The universe doesn't owe us anything, and yet, despite its complexity, it is possible to work out what the rules of the game are that allow us to understand how the universe came into being and how it ended up looking the way it does now. There's a flow of thought that we're going to follow here. We've known for 100 years or so observations of galaxies. We've known that they're moving apart from each other, relative to each other. It doesn't mean there's any particular centre. Every person in every galaxy will get the same impression that all the galaxies are moving away from them. So we come to the conclusion the universe is expanding. We've known this for about 100 years or so. We're also able to do experiments here on Earth. For instance, we can bang particles together, we can smash atoms in a Large Hadron Collider, we can take the constituents of atoms, the nucleus is made of protons and neutrons, etc., and we can get an understanding of how the world is put together. But we have to make some assumptions. We have to assume that the laws of physics at one place are the same as the laws of physics at another place. Simply because if that was not true, we would not be able to make any progress whatsoever. If the laws of physics in England were not the same as the laws of physics in Australia, we would have no way of understanding the way the world is put together. If the laws of physics here are different to the laws of physics in Alpha Centauri, or the Andromeda Galaxy, or a galaxy on the other side of the observable universe, we would have no chance of understanding how it's all put together. Similarly, we have to assume that the laws of physics now are the same as the laws of physics have been in the past and probably will be in the future. This talk is mainly about the past. So we have to assume that the laws of physics essentially have not changed since the universe was created. Again, if the laws of physics keep changing, if the laws of physics today are not the same as the laws of physics yesterday or the laws of physics tomorrow, then we have no chance of understanding how the universe came to be. So those are assumptions. The laws of physics are immutable. If we don't make those assumptions, we can't make progress. So they are assumptions, but they stand. If we take all of that together, we come to the conclusion that because of the expansion of the universe and our understanding of the laws of physics, it implies that the universe was created in a very hot, dense state some 13.8 billion years ago, and it has been expanding and cooling down ever since. So the question I'm trying to address this evening is, where did all the matter that we see today, all of those galaxies that seem to be full of stars and a fair amount of gas and dust as well, where did all the matter that we can see today come from? And we can ask the question, just how far back can we go before we have to say we don't really understand whether we can tell that the laws of physics quite definitely still held? Of the 13.8 billion year history of the universe, how far back can we go? Can we go back to the first year of the 13.8 billion year history and say, yeah, we're fairly sure the laws of physics then are the same as the laws of physics now? Yes, we can be fairly sure of that. What about the first day? Yep, no problem. What about the first hour? Yep, no problem. What about the first minute? Yep. What about the first second? Yep.
Yes.
What about the first millisecond?
Yes.
Yep. What about the first microsecond? What about the first nanosecond? Yep, everything's okay. What about the first picosecond? Well, no. This is about as far back as we can go before we have to say, hand on heart, we can't be absolutely sure we know what was going on before this point. Before the first picosecond, we are on somewhat shaky ground. Everything from that point onwards is relatively well understood. There's a watershed, if you like, at 1 picosecond. I'll explain why it turns out to be 1 picosecond in due course. So that was a rather long and unwieldy introduction to what it is I'm talking about this evening. I'm going to show one slide containing a few basic ideas which we're going to need in order to make sense of what's coming after that. And then I'm going to go through the first fraction of a second, the first few seconds, the first few minutes, and then jump, otherwise we'll be here all evening, for the next 380,000 years. Again, not an arbitrary number, there's a reason we've chosen that jump. And then I'll jump forward to the present day, 13.8 billion years later. Okay, so we need a few basic ideas, some of which I hope you're familiar with, some of which maybe not. I hope it comes as no surprise for me to state that we are made of atoms. And atoms are a collection of subatomic particles, a nucleus, positively charged nucleus, and negatively charged electrons buzzing around. So we can say that an atom is made up of some things that are smaller. An atom is not fundamental. You can break an atom apart and see what it's made of. It's made of a nucleus and electrons. As far as we know, electrons aren't made of anything. They are just electrons. They are fundamental particles. You can't take an electron, cut it in half, and have a look inside to see what it's made of. It's not made of anything. Unlike a nucleus, which is a so-called compound particle, it is made of something. We can take a nucleus and break it apart, and we find that a nucleus is made of some combination of protons and neutrons. And again, protons and neutrons are not fundamental. They are compound. They are made of something else. And we call those constituents of protons and neutrons quarks. It turns out that a proton is made of 3 quarks. Neutron's the same, but I'm just using the proton as an example. So these names, quarks, protons, neutrons, electrons, are just names that we give to the particles that we have discovered by trying to understand what matter is made of. But this sort of Russian doll approach that atoms are made of smaller things and those smaller things are made of yet smaller things, there's an implicit energy scale because it takes a certain energy to take an atom and tear it apart to make its constituent nuclei and electrons separate. And it takes even more energy to take a nucleus and separate it into protons and neutrons. And so it takes more and more energy to go further down this ladder, as it were. And remember, we came to the conclusion that the universe was made in a hot, dense state and has been cooling down ever since. And as far as physicists is concerned, high energy means basically hot and low energy means cold. Temperature, as in hot and cold, is really just a measure of how much energy the particles have. And therefore, there's an implicit timeline from the bottom upwards because the universe was made hot and is cooling down. That means the universe was made from the bottom up. If we imagine, can we make a nucleus as early as we like in the universe? No, we can't. We have to wait until the universe is cold enough for protons and neutrons to get together to make a nucleus. Otherwise, the universe has got so much energy, the protons and neutrons have so much energy, they will simply break apart and you can't make a nucleus. Similarly, you can't make an atom until the universe has cooled even further. Because if you try and put a nucleus and electrons together while the universe is too hot, they have so much energy the atom will tear itself apart. So things get built from the bottom upwards. This is the basic idea that hopefully will allow us to make sense of what comes next. So I guess we have to start at time t equals 0. And if we ask the question, what happened at the instant of time t equals 0, we have to admit that we do not know. Science cannot provide a definitive answer to what happened. There's plenty of hypotheses, there's plenty of conjecture, but none of them can be proved at the present time. It's widely thought that perhaps it was a quantum fluctuation, an energy fluctuation in which energy is borrowed from nothing. And energy, if you think of E equals mc squared, energy and matter are, as it were, interchangeable. So if you can borrow energy from nothing, you can effectively borrow matter from nothing. Yes, I know that sounds like a cheat. It sounds really weird. But let's face it, quantum mechanics, or quantum theory if you prefer, is weird. And that's the subject of a completely different talk. So to the best of our knowledge, quantum theory, which has been around for 100 years or so, and so far nothing has proved it incorrect, quantum theory allows you to borrow energy from nothing. So you can ask, well, how much can you borrow? How big can this fluctuation of energy be? Well, energy multiplied by the time you're borrowing it has an upper limit. A bit like if you borrow money from a bank, you can borrow a lot of money for a short time or a small amount of money for a long time and end up paying back a certain amount of interest. Well, quantum theory says there's a limit on how big energy times time is. So what matters is how much energy are we actually borrowing. Well, when you work it out, it's a tricky calculation to do, but you can look out into the universe and say, what is the total energy of everything that appears to be out there? All of the gravitational energy is negative energy. All of the mass energy is positive energy. And when you add it all up, the answer, we can't be sure, but the answer seems to be somewhere close to zero. So maybe we are lucky enough to be in a universe where we've got an awfully long time to pay back the loan. And yes, I'm sure you're not convinced by that argument, and this is still conjecture for reasons that I'll come to in a few slides' time. So what happened a little later than t equals 0? Well, after this ridiculously short length of time, the universe has expanded until it's about the size of a golf ball. And by the universe, I mean the observable universe. We don't actually know how big the universe is. All we can really say is what's going on within the observable universe, because by definition, that's all we can observe. At the moment, the observable universe is a sphere of diameter approximately 100 billion light years. But because the universe is expanding, and we can just wind the clock back and say, well, if everything used to be closer together, we can imagine a time in which everything that is currently spread throughout a volume of 100 billion light years, all of that stuff used to be separated by centimeters. So the observable universe used to be the size of a golf ball. And rather conveniently, just like a golf ball, the observable universe had dimples in it. Not physical dimples like a golf ball, little indentations in the surface, but it had dimples in the sense that there were small variations in density and small variations in temperature spread throughout the golf ball. That's the nature of quantum fluctuations. Eventually, a long time after this point that we're talking about here, these dimples eventually gave rise to the density variations that we see across the universe. The large scale structures that we see, the fact that we have a galaxy over there and no galaxy over there, for instance, that's a result of these tiny variations in density in the golf ball, which became exaggerated when the golf ball expanded to the universe we see today. We're now going forward to 1 picosecond after the Big Bang. The universe has expanded until it's now about the size of the solar system. Yes, of course, the solar system doesn't exist yet. We're just getting an idea of scale. So we're talking about a sphere that's now some light hours or so in diameter. But it's only taken a picosecond to get there. So clearly the universe has expanded much faster than the speed of light. It's allowed to do that. And indeed, it is still expanding faster than the speed of light. The temperature has now fallen to approximately 10 to the power 15 Kelvin. And this particular watershed point of 1 picosecond has been decided because at this particular point, at this particular temperature, the energy of each of the constituents of what I'm calling the quark soup, we've borrowed energy, we're allowed to make as much matter as we like, E equals mc squared, and that will be a combination of quarks and electrons and loads of other exotic particles, but to keep it simple, I'm just calling it a quark soup. Each of the quarks in this quark soup, each of the particles in the quark soup has got an energy which is comparable to the energy that we can produce in the Large Hadron Collider. That is why this 1 picosecond is a watershed point. From this point onwards, the universe is cold enough that the individual particles have an energy less than the energy that we can reproduce here on Earth. So in other words, any ideas we have about what's actually going on, those ideas can be tested because protons with this sort of energy are being smashed together in the Large Hadron Collider, and we can actually see the results of these experiments. Prior to this, the universe had so much energy we really don't know what was happening. Energy and matter continually exchange back and forth. We've borrowed energy and we're making matter. E equals mc squared. When we make matter, we make equal amounts of matter and antimatter. Antimatter being the close cousin of matter, the same particles with the same properties except they have opposite electric charge. Originally, matter and antimatter are made in equal amounts. I don't really know how to represent energy in a PowerPoint presentation, so I'm just going to represent it as capital E. So a certain amount of energy can be used to make a particle of matter and a particle of antimatter. It doesn't really matter what the particle is. So energy could make, okay, it's probably not going to be a tangerine and an anti-tangerine. It's probably going to be a quark and an antiquark, or an electron and an anti-electron. All particles of matter have an antimatter equivalent. Those matter and antimatter particles, after being made, will then annihilate and produce that energy again. That energy can then be reused to make another particle and an antiparticle. Not necessarily the same ones. It could make something completely different. Okay, probably not a hot dog and an anti-hot dog. It'll make something and its antimatter equivalent. Back and forth, energy to matter and antimatter, back to energy, back to another pair of particles. Pair of particles. Somehow, via a mechanism we really don't understand, matter gained an excess, a very small excess over antimatter. So although we expect matter and antimatter to be made in equal amounts, at this particular point in time there seems to be an imbalance. Of all the particles that were made, a smaller number of antiparticles were made. I've shown the imbalance here as something like 10% or something. It's not that big. It's more like not 1 part in 10. The imbalance was more like 1 part in a billion. But you can see what's going to happen. Matter and antimatter are going to annihilate to produce energy. That energy will normally be in the form of electromagnetic waves, so gamma rays flying around the universe. But what's going to happen to that Satsuma on the right? Well, it's got no antimatter to annihilate with. Some particles have been made that do not have antimatter equivalents. So they are not going to annihilate to just produce a universe full of light. We are going to end up with a whole load of energy, a whole load of radiation, a whole load of light if you prefer, and we've got a universe that's full of light and a little bit of matter is left over. And that matter is everything we can see in the universe. That's every galaxy, every star in every galaxy, every speck of dust, every molecule or atom of gas that's floating around. And of course, it's Earth and you and me. So it's just as well there was a matter-antimatter imbalance at this very, very early time in the universe. We're now moving forward to 1 millisecond after time t equals 0. Matter and antimatter are continuing to pop into and out of existence. Protons and neutrons can be made from their constituent quarks. And we don't have to worry too much about the details, but quarks come in a lot of different types. I've labelled them here with the letters U and D, and I've coloured them red, green and blue. We are not going to worry about why I've labelled them like that. All that matters is if you make a lot of quarks, some of them will get together, and a bag of 3 quarks that looks like what's on the left is a bag that we call a proton. And if those 3 quarks get together such that we end up with the configuration shown on the right, well, that particular bag of 3 quarks, that's what we call a neutron. But the universe is still hot, which means that energy can make quarks and quarks can annihilate with antiquarks and make energy. And that means quarks can keep transforming backwards and forwards into different quarks, and hence this configuration can continually change. That means that protons can turn into neutrons and neutrons can turn into protons because the individual quarks are changing. So although I'm going to label protons as little red spheres and neutrons as little blue spheres, at this point in time they are currently continuously changing backwards and forwards. We're now looking at 1 second after t equals 0. The universe is now cooled to about 1 billion Kelvin. At this point it's calculated that it's too cold for protons and neutrons to readily swap backwards and forwards. We need a certain amount of energy to do that, a certain amount of temperature in the universe, and the universe is now getting a little bit chilly. Protons are a little bit lighter than neutrons by about 0.1%. How do we know that? Well, we've measured it in the laboratory, and we believe that a proton now is the same as a proton was billions of years ago, and the same for neutrons. So if protons are lighter than neutrons now, then we think they were back in this particular era. So if neutrons are heavier, when the universe makes lots of neutrons and lots of protons, it makes more protons than neutrons. Protons outnumber neutrons in the ratio of 75 to 25. That ratio can be calculated based on the temperature. You might ask, well, why does the universe make more protons than neutrons? Well, it's because nature always favours the lower energy, or if you prefer, the lower mass. It's like saying, if you're going to make a whole load of protons and neutrons, protons have got lower mass, so they're easier to make, and you'll make more of them. And it turns out the ratio is that 3/4. I've shown here a representation of 16 particles, of which 12 are protons and 4 are neutrons. If we go forward to 2 or 3 minutes after t equals 0, well, we know that neutrons are unstable and some of them will change spontaneously into protons. How do we know that? Because we can see it happening in the laboratory. We know that neutrons are heavier. Heavier particles can change into lighter particles. It takes neutrons about 1/4 of an hour or so to change from one to the other. So the ratio of protons to neutrons has now changed at this point. Instead of being 12 to 4, it's now 14 to 2 for this representative batch of 16 particles that I'm looking at here. And this ratio of protons to neutrons is now essentially fixed. The universe is too cold to change that. But what can happen now is that protons and neutrons can now start pairing up. Protons and neutrons would really, really like to get together. And the most stable structure that protons and neutrons can make is this one. It's called an alpha particle, 2 protons and 2 neutrons. Once the universe has cooled to about 100 million Kelvin, we can now make the nuclei of atoms, because this particular combination of 2 protons and 2 neutrons is what we call the nucleus of helium. It's also called an alpha particle, but in this context we're going to refer to it as the nucleus of a helium atom. And you can see that once we get 2 protons to marry up to 2 neutrons, all of the other protons haven't got any neutrons to pair up with. They're going to be left as a whole load of bachelors. So we end up with 12 protons, which again we're simply going to think of as the nuclei of hydrogen atoms, and 1 nucleus of a helium atom. And from this point onwards, that will not change. After 3 minutes, the relative abundance of hydrogen and helium has been determined. That's why we say the universe was made in 3 minutes. Everything that happens from this point onwards is simply a rearrangement of the protons and neutrons. Stars might fuse hydrogen into helium and fuse helium into carbon and fuse carbon into heavier elements, but that's just a rearrangement of all of the protons and neutrons that we see on the screen at the moment. So Big Bang theory predicts that if this is right, if this is where all the hydrogen and helium in the universe has come from, then we look at the mass, we should find that the universe has got 3/4 of the mass of hydrogen and 1/4 of the mass of the universe should be helium. What do we actually find? If we look out into the universe and we try and estimate how much hydrogen is out there, how much helium is out there, we find that the ratio is 3/4 to 1/4, exactly the same as the ratio we would get from the mass of all of this hydrogen and the mass of this helium. That's one of the key reasons that we think Big Bang Theory is correct, because it does explain the ratio, the abundance of hydrogen and helium. There's also a tiny amount of lithium, but we're not going to go down that particular avenue this evening. We're now going to change gear somewhat because we've got to move forward, and we're going to move forward 380,000 years. And that's because nothing very interesting happens for the next 1/3 of a million years. The universe continues to expand and cool. In other words, we've still got the same amount of hydrogen and helium nuclei floating around, and we've got a few electrons buzzing around as well. And they're doing nothing other than getting further apart and cooling down. But at this point, 380,000 years after t = 0, the universe has cooled to a temperature of about 3000 Kelvin. Why is that temperature relevant? Because at this temperature it is possible for the nucleus that we've been describing, like hydrogen or helium, to actually hang on to the electrons that would be buzzing around it to make atoms. So this is the first time in the history of the universe where we can make atoms. Up to this point, the universe has been too hot. If you try and put electrons around a nucleus, even though the nucleus is positively charged and attracts the negatively charged electrons, it's simply too hot and the atom shakes itself apart. But now the universe is cold enough for atoms to exist. So instead of being a collection of positive charge and negative charge floating around the universe in a plasma, an ionized plasma, we now have a collection of atoms that are neutrally charged. Each atom has no net charge. And for the first time in the history of the universe becomes transparent. Up to this point, any light that was rattling around was simply getting scattered by this plasma of positive and negative charge. But now the universe is transparent, the light is free to fly across the universe. And we see that light today. At 3000 Kelvin, the universe would have been white hot, so there would be a huge amount of ultraviolet and visible light. Visible light has got a wavelength of order microns, thousandths of a millimeter. But since this point in time, the universe is now some 1,000 times bigger. The universe, of course, has been expanding ever since t = 0. Didn't stop expanding at this point. It's been continuing to expand ever since, and it is now 1,000 times bigger than it was at this point. So if at this point the light had a wavelength of order microns, and then you stretch the universe 1,000-fold, the light will have a wavelength of order millimeters. So we won't see it as visible light. Because of the expansion of the universe, we see it as microwaves. And that is why we see the cosmic microwave background. This is the entire sky, unwrapped as it were, or unwrapped and then projected to give us an idea what the sky looks like. Microwaves are coming from all directions because, in a sense, the universe was born in all directions. Basically, remember, the Big Bang didn't happen at one place, it happened everywhere. So although the universe is bathed in microwave background, it's not perfectly uniform. This is exaggerating the tiny differences in microwave intensity. Some parts are just a little bit more intense in microwaves, some parts are a little bit less intense in microwaves. And this is effectively the dimples in the golf ball that we saw quite a few slides ago. Small variations in density and temperature when the universe was the size of a golf ball. Those small variations in temperature are still there many thousands of years later, and that's what we see imprinted in the cosmic microwave background when eventually the light was released to fly across the universe. So it's rather important that we look in detail at these small variations in intensity that we see in the map on the previous slide, because they're telling us about the dimples in the golf ball. So if we can study those variations, it gives us a very neat way of studying the very early universe. That's why we're taking great pains to have satellites that map out the cosmic microwave background as accurately as possible to see what these variations look like, because it gives us this unique insight into the very early universe. I've said that the dimples eventually give rise to the density variations that we see today. It's a little difficult to imagine that from something the size of the golf ball, but if we take a simulation, and the web page at the bottom tells you where you can find some of these videos of the simulations. If we take a chunk of the universe, not the entire observable universe, but a chunk of it, fill it with matter, but put in small variations of density and temperature, hence the blue colour you can see here is slightly mottled because the shade of blue tells us about the density of matter. If we let gravity do its stuff over a few billion years and ask, what does this look like? Well, we see that gravity takes hold of the denser regions and makes them even more dense, bright in this particular representation. Notice that the relatively uniform density of the early universe is now becoming very, very different. We now have a web-like structure in which we have white knots which represent galaxies and clusters of galaxies and superclusters of galaxies. And these galaxies are not randomly distributed throughout space. They seem to occur on these lines, on these filaments of this interconnected web, which we can think of as the cosmic web. And there are some regions, like the region in the top right, for instance, which are quite dark in this representation, which appear to be relatively sparsely occupied. This is just like we see in the universe when we look at where are the galaxies. Remember that fly-through of the 3D atlas that I showed very early on? This looks very close to the sort of structure that we see when we map out the galaxies in the universe. Here's a representation of what the immediate vicinity of the Milky Way looks like. There's the Milky Way galaxy labelled, surrounded by a few very small satellite galaxies, dwarf galaxies. We've got a few dozen, perhaps even a few hundred tiny galaxies around us, and there's the Andromeda galaxy over on the right. This is the local group of galaxies. If we change scale and shrink that down and look at a larger scale, we see that our local galactic group in the middle there is one of many galaxy clusters. We've got the Virgo cluster out on the right hand side here, and we've got other clusters. Notice that these clusters are roughly speaking in a line. There seems to be a filament joining together lots of galaxy clusters, whereas there's relatively few in the top left and not that many close to the bottom of this particular volume. And if we do the same again, shrink this down and look at a slightly larger volume of space, we are again right in the middle there, next door to the Virgo supercluster, and we have other superclusters dotted around. Again, we see this web-like structure on the largest scales. And over on the right-hand side, we see some regions in space which appear to be relatively sparsely populated. This is all a consequence of the fact that in the original cosmic golf ball there were small variations in density which over many billions of years ultimately produce the density variations that give us the galaxies that we see today. So again, let's change gear. What happens in the next 13.8 billion years? Well, you could argue that if in 3 minutes we can understand where all the hydrogen comes from, we know that the hydrogen feeds the stars. Stars take hydrogen and start fusing hydrogen, releasing energy and hence heat and light. And releasing that energy to allow planets to bathe in that heat and light, and hopefully life to evolve. You could argue that if in 3 minutes we understand where all of the hydrogen comes from, then that's really all we need. Because if we understand hydrogen, then we understand galaxies, and we understand stars, and we understand planets, and we understand trees and mountains and snowflakes and rainbows and cats and... Okay, maybe not cats. I'm not sure we'll ever understand cats. But if we understand where all the hydrogen comes from, then yes, there are still some details of cosmic evolution yet to be worked out. But cracking the where did the hydrogen come from in the first place allows us to get some handle on where all the stars come from, where all the galaxies come from. Let me just give you a graphical summary of what I've been telling you on a rather silly scale, from ridiculously short times on the left to the present day. So hypothetically, we think the universe was the size of a golf ball after a ridiculously short length of time, and those small variations in the density ultimately gave rise to galaxies. We borrowed energy from which we make matter, and we've made all sorts of quarks. Doesn't matter what types of quarks. We've also made loads of electrons, and we've made loads of other particles as well. Doesn't matter. Let's just call it a quark soup. We've borrowed energy to make lots of quarks and antiquarks and other stuff. After a short time scale of order seconds or so, we can start making protons and neutrons by those quarks getting together. And a proton and a neutron are just the names we give to a bag of 3 quarks of a particular type. After a few minutes, those protons and neutrons can get together to make atomic nuclei. 2 protons and 2 neutrons make the nucleus of helium, and any bachelor protons that are left are what ultimately will become the nucleus of hydrogen atoms. Those atoms will be made after 380,000 years, when eventually the universe is cold enough for the electrons to be caught by the hydrogen and helium nuclei. And at that point, the universe becomes transparent, and we see the microwaves flying across the universe today. There was then a period, we're not too sure exactly how long it was, after the microwaves were released. It took a little bit of time to make the first stars. Was that 100 million years? Was it 500 million years? Well, one of the reasons we've launched the James Webb Space Telescope is to give us an idea of how long did it take from t = 0 to make the first stars. We think the answer is a few 100 million years, but we're not too sure exactly how that works. It seems to be a process that operates faster than we first appreciated. What we do know is that in the next few billion years, the stars and the galaxies were born, and that takes us up to the present day. Now, I admit I have glossed over a few things. The jigsaw of our understanding is still not complete. There are some fairly fundamental questions still remaining. Why did matter win over antimatter? We are fairly sure it did because we are here and we're made of matter. We look out into the observable universe, it appears that every galaxy in the observable universe is made of matter. So why did we end up winning over antimatter? What caused the asymmetry? And I've been trying to be very careful when I talk about everything and the beginning of everything. I mean everything that we can see. All of the galaxies, all the stars, all the gas, all the dust. But that doesn't include stuff we can't see. There appears to be dark matter out there. We can't see it, but we can see its effect. It seems to be causing galaxies to rotate at speeds that we wouldn't expect based on just the visible matter. And in the last few decades, we've become aware of what we are labeling dark energy, and we don't really know what it is, but it appears to be causing the universe to accelerate its expansion, even though we would have thought gravity would start to slow the expansion of the universe after a certain length of time. So this talk is titled The Beginning of Everything. But as I've just said, I'm talking about everything that we can see. Everything in the universe is not everything that we can see. All the ordinary matter, all of the luminous matter of the universe only accounts for some 5% of the total budget of the universe. The other 95% is still a bit of a mystery. But, as they say, that's another story. Thank you for listening.